there might just be a few minutes of silence. But yeah, thank you for saying that. And actually, I'm going to move this a little bit so it gets everybody more. Thanks for catching that. And Josh, yes, I do like your typo catching.
Okay.
And if you want to just put that on the actual sheet and hand it to me, that works too. If you don't want to, if it takes more time to type it up with that.
Okay.
So I appreciate that. Not sure if this is ever going to turn into a textbook, but I'd rather have the typos out as I find them. So I appreciate that.
All right.
Cool. And then Thursday we're going to do a little more just thinking about stress in a body, which will feed into your the last problem in the problem set. And I know Joshua wanted to talk with me a little bit about index notation after class. Are you okay with other people jumping in on that discussion?
I'm okay.
So yeah, if you guys do have some more questions about the index notation stuff, then we're gonna try to get that going. And so the one other thing I wanted to say about the computing, each of the computing assignments now will be are each going to be 2-week units, 2-week computing, so they follow along with the 2-week units. So you'll do 6 of them, and the way the calendar worked out this year, because they started us early or something, I don't know. There's some various things didn't happen, and Jeff and I always look at this because sometimes he travels and sometimes I travel, and we have to adjust the schedule to fit that. And right now, just so that you know, there will be no classes there will be a computing class on Monday, but not a Tuesday and Thursday class the first week of October, like October 3rd and 5th or something like that. And that ended up working out because of the way the schedule worked with the university. But just so that you guys know, I have a conference that week, and Jeff has some other conferences, so that just seemed like the easiest to basically take a break for a week at that point. But we will have the computing during that week. So that's how I was able to bump yesterday's computing, because I knew that we had an extra Monday in there that was still free. So jumping into this Thatcher article, I want to try to keep our discussion to a half an hour to 40 minutes maybe. And what I want actually to start with, there's the introduction section, and then there's 3 sections about it. There's the first one is called Microplate and Continuum Models. The second, wait, is there 4? I can't remember. Then there's application to active tectonics.
Sections.
Fault slip and block rotation rates. And then the forces driving. Oh shoot. Is that 5? I thought I was figured out. There's the intro. That first one is only the micro plate one. And there's application. And the fault. Rotation rates. And then the forces. I think at the end there's just this one. I wanted you guys to get into I thought I had this divided up, but we are going to do, yeah, we're gonna do this, and this. So I do ask you, you guys will a lot of times do something with each other, and if you always sit in the same spot and you always turn to the person that's next to you, then you're always gonna be talking to the same person. So you can either voluntarily sit in a different spot every class, or we can get up and move around some. And I think you guys all worked with the person next to you last week, right?
I wasn't here.
You weren't here. Okay. Well, maybe we can make this work. But I want so starting here, 2 people. Although you guys worked together last time, didn't you? It doesn't matter.
I was
that
sat
much.
over there.
Okay. Yeah. Great. Perfect. You guys we're gonna start with the intro and the microplate sections, and then the 2 of you back there will do the application and the fault slip rotation, and then the 3 of you are gonna do the forces. And what I want you to do right now is just take about 5 minutes, and as a group, come up with like 2 of the main key points from that section, and a question that you have, or a question that you guys have related to it. And that'll just get each, and then you guys as kind of a team will be leading a bit of that, the discussion part of that. So 5 minutes, and then we'll come together and discuss each part.
It was on Blackboard.
I can't remember.
Yeah,
I didn't read all of it. I'm glad we did that the first one because I remember reading from the introduction.
yeah, it was a good thing I started to work on some homework. yesterday.
Aaron?
I looked stuff
Yeah.
up 'cause I
This
saw
is the reading you posted on Blackboard, right? Not
since
this
I
one?
was there.
Yeah, it's the one I posted.
didn't
It's not
see that
this one.
yesterday.
Oh, sorry, it's the Thatcher reading I posted on Blackboard.
Oh.
Yeah. This one, I also said right before you came in, is just a little supplement optional
I've been
reading.
kind
So
of
it's a
crappy
cool
with sick
paper
this
Okay.
weekend, so
by
I
a
can't
former
remember
UAF
anything I've
student
done.
on
I'm gonna be honest.
I feel like I read the intro to this, but not.
Okay. So, I read this one.
The intro was all about the block method and the
Yeah,
other one.
so we're supposed to mention I guess the main point. So it was talking about the block
One of the
method.
biggest points about that section was differentiating between,
Yeah, velocity field.
I guess, continental and local forces.
Yeah, and adjacent.
Yeah, the local forces
sections. I remember
are
reading this.
for the continuum model, right? And the block model
That
are
that
the
there's a lot more
the continental forces.
data available with satellite imagery and
Mhm.
GPS. But
Okay, let's come back together. And
I guess we're just talking about like the differences between the two because that's what this whole section is about.
go
Yeah.
through,
I mean,
go through each section. We'll spend just about between 5 and 10 minutes on each section, kind of as needed. So do you guys want to start with what you found were the big ideas presented in the intro, and then that micro section?
well, I mean, the introduction was sort of talking about difference in block and continuum models
Yeah.
and how you quantify deformation.
Yeah, I think
Do you
one
want to
of the-
explain what you,
Kind of
how you interpret
mix.
the difference between a block and a continuum model?
Well,
Yeah, so the block model making these sort of surface blocks that are sort of pressed up against one another, and it
have specific boundaries, divide
Yeah.
them up into these sections with boundaries, how they interact.
it assumes these brittle blocks pressing up against each other. Yeah, where's the
Pretty much deal with that.
whereas the continuum model looks at the whole plate all the way through, and just looking at the forces all the way through.
Yeah, I guess it looks at it like as a whole, and how you apply the deformation or the stress or whatever through the whole plate, whereas the block just sort of smaller parts. I know that the continuum model worked best with like the lower ductile parts, and the lithosphere, and then the block was for the surface, the very brittle parts. Could quantify deformation a little better with that.
So the deformation is distributed in the continuum model across the whole area. Is that that's sort of what I heard you say. And then it's the lower crust is the ductile one.
Yeah,
right?
you look
And
at the
Yeah, or if lower crust is more ductile, then the continuum model is a much better way to describe it, or describe what's happening.
Right, yeah, I think he kind of comes to that point at the end where if you think that the lower crust is controlling most of the processes, then that's the way to
And
go.
another just sort of point from the intro was that this has only become an issue recently when with satellites we're able to actually take much better data than we have been before, and so we're able to actually to really look closely and get a lot better at validating some of these models.
Right, before we had satellites and high resolution GPS, we didn't have enough information to really know what that distributed deformation would be like. Yeah, that's a really good point. And what was the question that came out of? And what else? I mean, I guess I want to hear from everybody on kind of what they found in that first section. These guys are. How many of you guys actually read it? Okay, good.
I ended up just skimming it. I feel like after I was sick and all that, I'm
Maybe
just
that's the time.
behind.
Alright, I want to hear what you guys think. Come on, let's talk. I'm going to make you talk in this class. You might just get used to it. What's Josh?
Speaking of continuum model, like how small we can agree on, like if we look at this let's say this microplate, and you know, inside that microplate we can also make another continuum approach, such as like type of rocks can have different behavior, like when we apply forces such as shear forces, or so like how small we can agree on.
Go with the
Yeah.
That's kind of his figure 3. Where he keeps dividing it up
If
into
you take
smaller
the-
and smaller chunks.
If you take the block model to the limit, it essentially becomes
It
a
becomes
continuum.
a continuum model. Yeah. So if you find yourself chopping it up more and more because your data requires you to chop it up, if you start with the block model and you keep making it smaller and smaller and smaller, when would you switch to the continuum model?
Well, it depends on the consensus, like when all people agree on like specific things.
Okay, so you might look to other people's work and try to figure out what the community would do under a
Yeah.
certain situation. What else might it depend on?
Like the resolution of any other data that you're working off of.
Yeah, it'll depend on the resolution of the data that you have, and if you start to, if you need to go so small in order to match your data, then it might be worth switching. And
One of
then-
the things I was wondering, and maybe new to like plate tectonics and things and like that. But I was sort of wondering like, shouldn't the continuum model be something you apply when you want to look at like a plate as a whole, or even beyond that, and you want to see like where the force is coming from and like why are these things, you know, more of like why are these things being driven where, and I was wondering if maybe the block model is then better for like what's or a good approximation for asking like what's happening right here. And maybe I don't like haven't, you know, fully completed my understanding of the difference between like brittle upper crust and ductile lower crust. But
no, but you bring up a really good point, actually, the third one that I was thinking of, which is it depends on the question that you're asking. And so what you might do is you're thinking about your question, you have this data set, you may or may not need to go down to the resolution of the data set. Your question might allow you to stay in the block model even if you have data that goes finer than that. And then you might look to the community to be, well, this, based on the question that I have, what have other people done? What does my data allow me to do? And then decide. And you might agree with your community and you might not. You might think that you can solve the problem differently than the rest of the community. He says at the end, very, very end, he says that there's still a lot of debate in the community about this. And there's actually, there's a fourth thing that I might consider.
Processing power?
Yes, processing power. Because if you need to do a big continuum model, it can really start to suck. You know, unless you have a supercomputer, you might. So yeah, that would be kind of the fourth thing. But coming back just to kind of make sure that we're all on the same page here. So the continuum model is when our deformation, or at least we want to understand the deformation more in terms of how it's distributed over area, whereas the block model is where it's localized on specific faults. And this one, I liked this one about thinking about the lower crust versus the upper crust. You know, he sort of comes back to that later on as well. In that, I can't actually do that here, since the upper crust, it's a neat little cross section. The upper crust here is much more brittle, it's more likely to fracture. The lower crust is going to do more oozy deformation. And how deep that transition is depends a lot on where you are, what the particular area is like. But his point is, so if you can imagine if this lower crust is kind of weak and really squishy, but that fault has a lot of friction on it, then the friction on the fault might play a bigger role in determining the overall, basically the limiting factor in determining how much and how fast and how often this thing moves. Because the ductile crust will it's like, I'll just do whatever you say, you know. The crust is, if the brittle is in control, then the block model might be the more important thing, because then you know that it has to do with that all of the question of what it does happens in that upper crust. But if this is a little bit stiffer and this is a really, really weak fault, then it might be totally dominated by the deformation down here that's controlling everything. And that deformation might be distributed out over, you know, kilometers on either side of this, even though at the surface we only see the little weak fracture points. So I think that difference in terms of the strength of the upper crust versus the lower crust is again, it depends on your question and all these other factors too, but that can be a really critical piece. And then there was kind of one other big difference between the two in terms of the assumptions that you might make. That sometimes if you don't know enough, you might need the block model to begin with. And what piece of information is that is really important for the continuum model?
You have to know the what the rocks, what the material
Yeah, rheology.
of the rock is,
Yeah,
the rheology.
and that's in his figure 2, where you've got this whole distributed network of forces that, given their rheology, will give you a certain distribution, and this is what you measure. This is something you have to kind of assume based on the properties of the rock, so that you can get back at understanding what the forces are. If you really have no clue about what this is and you just decide to give it one number, then you sort of have to question whether or not there's much value in going all the way to the continuum model, because you're putting this artificial uniformity on the block anyway. So that having some knowledge of what the rheology is an important piece of that. Okay. So then the second part, the application and the rotation stuff, he goes into a little bit more detail. What were some additional kind of key points that you guys got out of it? Or mostly that you did, since you didn't have time to read the whole paper, that's fine.
The block model will be better for short-term problems. It usually works better on less than about 10 million years. And if you're looking at something like plate tectonics, which you can be looking at timescales of hundreds of millions of years, a block could become completely deformed into a new shape rather than fault.
Yeah, that's a really good point, that this is short-term questions that involve short-term behavior versus long-term behavior. Because your block is only going to exist as a block for a certain amount of time before it gets subducted down or whatever happens. I think that's a really important one. What else did you guys find out of that? Any good examples that you noticed or interesting?
One of the other things I came away with was that the block model can work. Sometimes it can work well, and there are a lot of times where it doesn't perform any better than the continuum model on short-term problems.
But that's when you might think about your processing power and the computing, because this one is going to take more computing. So even if the block model doesn't work any better, it might be easier. Because really, I mean, the continuum model should almost always be better in terms of the result you'll get out of it if you but not. What else? What else did you guys get out of this section?
There was one or two times where, do we want to?
Yeah, keep going.
Where they said that with the block model estimating or predicting motions that didn't match anything even with deformation that they'd input. Yeah, predicted fault
Sometimes
motions
you
that didn't
get
agree.
wildly
It
wrong
didn't agree with
answers.
anything that.
Yeah. Yeah, sometimes wildly wrong answers. The first computing assignment you did that Jeff put together, that was calculating rotation rates and
Yeah.
trajectories of. Was that assuming the block model or the continuum?
Block model.
Yeah, that was a block model. What else? Did you guys have a question that came out of that those middle sections?
Not really.
Not really.
I don't know enough to ask anything.
And then this final section, what did you guys see as being his main points in the final section?
One of the key points was pointing out the differences between continental forces and local forces and how you're lumping them, grouping forces together as opposed to taking them kind of as each their own influencer, I guess would be the word for it.
Do you wanna provide an example?
Well, like, I know he lists 6 or 7 subduction zone forces, and how each of them will influence either slab at different depths at different rates, but then often they're just combined to trench normal and trench parallel, if you're looking more at kind of a surface thing, whereas with the continuum you
can
look at like the rheology of the plate, of
Right.
the subplate surface, and that makes a big difference because the range of those forces is quite vast, and when you lump them all together, it's kind of makes a pretty big error bar, I would imagine.
Yeah, I think it can lead to confusion when you are piling several different processes that might be acting on different timescales, but you lump them all in as one set of forces with one set of reactions. I think that's a pretty important point, and this comes back to thinking about what are the questions that you're asking, and if the question is gonna be affected by the different types of forces that might be causing deformation, then the block model is not gonna help. Yeah, I think that's a really good one. Did you wanna say?
Yeah, I have questions
Mhm.
for this part. So suppose that in block models we combine all these small forces into one big force, like in the slab pool area,
Mhm.
and when we calculate that we get the uncertainties, and suppose if we go towards the continuum model and we will get the uncertainties as well, and I wonder like the difference between the two uncertainties, like how big they are, like in a real world
Yeah.
example.
I mean, it's a good question, and it might depend on how well you actually know the forces in the
Yeah.
region that you're interested in, and again, this comes back to, I mean, that in a lot of geophysics, there's so many unknowns that we end up dealing with that it's always best to start with the simplest model that you can, given what you know about the system. Like, don't make it complicated if you don't know what information to put into the complicated model. Garbage in, garbage out, right? So if you you say that there's all these different types of forces and you're just guessing at the distribution among those forces, then it might not help you at all, and your uncertainties aren't necessarily going to be improved at all by going to a continuum model. So yeah, it might be a location and information specific thing, but it's good to think about like what the uncertainties might
Probably
be
also
in
time.
that situation.
Also time.
The time, yeah. If you're
How long was that?
what time scales you're interested in.
Yeah.
So what are these different forces that we might be separating out? Just to kind of do a little, I think he does a nice job of kind of outlining the different forces that are happening within the continental plates.
Slab pull.
Slab pull. And what ultimately drives that? I don't know how much he goes into that.
The increased density of the downfalling slab.
Yeah, so when a slab starts to go down and it's this cold, heavier stuff that's going into the mantle, gravity just starts to pull it deeper down into the mantle, and that will pull the whole plate because it's all connected.
There's also the eclogite phase transition at around 100 kilometers, which increases density more.
Yeah, good point. There's transition. Cool. What else?
Drag force of the lower material or plate.
Yeah, so if this is moving in either direction, left or right, there's going to be some kind of a drag force from the mantle material underneath it. So that's a shear force on the bottom of the plate. Slab pull is a normal force that acts along the axis of the plate. Good. What else?
There's a force due to corner flow in the wedge, the asthenosphere that's right below the slab. Or
Is
above
that-
the slab, my bad. Above the subducting,
This
below
one
the
is what this
below, yeah, that little corner there,
that corner.
down below that arrow.
There's which one are you? There's that it's pulling this down, right? Is that what you're talking about?
This is the corner flow that's
Yeah. Is it-
in the little wedge part there. So it's asthenosphere that's
This stuff.
sort of, yeah, so it's
That has to get
convecting or whatever. So it's just going a little. Generally, that's in the
moved. Right.
subduction
Oh, right.
models.
Yeah. So it's doing this.
Yeah,
Mhm.
yeah.
Yeah, that's right.
And then, so that's driven by the subducting slab, gets it
Right.
going, and then it just sort of adds to the pulling it down.
Yeah. So that corner flow just kind of seems like it's a bit of a variation of the drag flow, but in a specific area. Okay, what else?
Thickness and density distributions.
Yeah. Which I think and we'll call it in this class often, it's because it's due to the gravitational potential energy differences. You have high mountains and low mountains. Like the ball of silly putty that you put on a table, it's going to want to spread itself out. So high mountains will spread out towards low mountains. And that actually is, I think that's the question, one of the questions that I gave you in this, in the homework problem set is thinking about the difference in two floating plates. What's driving that? And that's literally just high mountain to low mountain it's gonna wanna spread itself out. Good. What else?
Unusually buoyant lithosphere. So that's, I mean, that kind of goes with the other one, just the thickened
The thickened
crust.
Yeah.
So
Let me go through here. The other one that jumps out as, there's a couple of different ones, but ridge push. How is that different than slab pull?
So when your ridge is
I mean, it's-
spreading, then it's going to be, of course, as it's forming at the ridge, it's pushing the rest of the crust away from it, and so it's pushing it essentially into the subduction zone.
Yeah. And a push is sort of different than a pull, because
Yeah.
like when you push on something, it wants to like spread out as it goes, whereas when you pull it, you're like bringing it towards the one area.
Or compression rather than the tensional.
Right, so you're putting compression, a compressive, as opposed to pulling from that end. Yeah, and so it's just due to these spreading centers. And I think there's a lot of places where it's not clear whether ridge push or slab pull is dominating a particular system. And I know that there's still arguments in some communities about some places, but they both are probably active in some ways, but I think there's still a lot of
I've heard people argue that slab pull isn't even a thing. They believe
And-
it's all pushing. All
yeah,
pushing from
but
the
I think
ridge.
I've also heard that the opposite, in that if it's mostly slab pull, then you're kind of sucking this material up
Yeah, and
the
so it's
other
having to
end.
make more to keep up with that.
Yeah,
the
exactly.
good old conveyor belt.
Wouldn't it not form ridges like that, like some of the bigger ridges, if it's all
If it were
slab
just
pull?
sucking.
If it's all pull, yeah,
Yeah.
because it would
There
just
would
stay
be no
sort of
ridges.
flat.
That's
There would be no
probably
build
true.
up
It
It would
on
be
the
pulling
ridge.
it up out of the
It would be
asthenosphere.
like
Yeah.
It'd be ridge pull.
Exactly.
Slab pull and ridge pull.
It wouldn't have time to build up into a
it
ridge
wouldn't
like
have time
that.
to build up. Yeah, that's true. That's
So-
true.
It's all pushing. There's
It's
no
all
pull.
pushing.
Then it should be like a carpet when it hits the content. Wouldn't it?
Oh man, slab rollback. Oh, that's a.
Yeah, I read that, but I didn't bring it up because I didn't
That's one that
understand
I
it.
don't.
I think that's when the slab starts
Yeah.
to do this.
Yeah.
Where does that
Because it starts to sort of
happen very?
steepen or something. Isn't
Yeah.
that where it?
It's
so
like
the
if there's
trench-
a especially dense oceanic crust
Yeah,
subducting.
So
Yeah.
the trench moves back.
Yeah, and
Trench
I
moves
think
back.
trench rollback is what I
Um,
normally hear it talked
Instead
about
of
as.
slab rollback.
Yeah,
Yeah, I think I've heard it.
I
said
don't
maybe that's where my
remember what-
confusion was.
what causes it, but the example I always think of is that, or at least I think this is an example of that, that the basalts in Idaho are from when the Wanda Fuca plate was going down at a shallower angle, and the volcanism was centered more in Idaho, and then it dropped down, and that's why the
Migration.
Cascades
Hmm.
are over here, and I'm not sure exactly
Hmm.
what drove that change, but there's a big jump between the former volcanism over in the remnants over in Idaho and in Cascadia.
Wasn't
But
it because of a hot spot there? What I guess is now
well,
the
Yellowstone is a hot spot,
Yeah.
but that's
Well, wasn't that the volcanism? Or are you talking about different?
Well, I
volcans
thought it
over
was
Idaho?
different volcanism because the Yellowstone hotspot did move, but I thought
Yeah.
there was a whole bunch of basalts there that I thought were more.
And I think they might be
Because Craters of the Moon was
like not all one thing, not all the other.
National
Like a lot
Monument
combined.
is definitely
remnants of the Yellowstone hotspot.
Craters of the Moon is.
Yeah.
That could be. It's been a while since I've
So we're not sure why it would suddenly sort of steepen, because I know like in South America you have a whole plate and some of it's steep and some of it's shallow. It's
Yeah.
the same. So it can't be with like the material of the subducting plate if it's all the same material and some parts are steep and some parts are shallow. So I mean, I guess what would is it the surrounding
One
material?
like overriding plate.
There could be
What
some
part of
dependence
Oh, the
on the age-
overriding.
On what?
on the age of the plate. So
The
if it's a really
age,
old,
yeah,
it'd
I
be
do
slightly
think the
different.
age plays a difference. Plays a role in it. And
I
then,
guess that makes sense.
And also,
It's
like,
coming
if
in
you
at an angle
have-
in South America.
Like any, and I don't know if this is true or anything, but if you have any like transform faults that had formed closer to the spreading ridge, once those start getting subducted, that seems like that would be a place where
Oh, I think-
preferentially you would have a plate split.
Yeah, I did hear that
And then-
sometimes they sink if it breaks off, or it starts to break off, and so it looks like it starts
Yeah.
to sink
Right.
more. I've heard
And I-
that before, but
Yeah. I don't know
All
if
sorts
transform
of-
faults
all sorts of
come back
funky
out then,
mantle stuff
Yeah, I have a-
going on.
nonsense.
but no one can see it, so we can make up anything
We
we
can
want.
say whatever
Yeah,
we
I have
want
a- I have
about
a
it.
more basic question. When does, like, as this plate goes into the mantle, when does it, like, stop being connected to the plate and just becomes part of the mantle?
Become oozy part of the mantle.
Good question.
Yeah, it is a good question. I know it goes through a lot of, it starts warming up, so it starts to match the temperature, but then it goes through phase transitions and, but I don't know, I see these, I'm not a deep earth mantle specialist, that's for sure, but I've seen these pictures where they see like lumps of stuff at the, in like within the D double primary, there at the core mantle boundary that they think are the leftover little plops of the plate.
Yeah, some
Okay.
people argue that it subducts all the way down to the core boundary, and then it starts to
get-
melts and mixes in with the other.
Hmm.
But then others say it always breaks off somewhere in the middle. But I just we don't know.
No, we don't know. I think
We need a better X-ray of the Earth.
it's got a different composition, so it's going to take a while for it to mix
Yeah.
together. And,
Okay.
but that's about the extent of my knowledge of the chemistry down there.
Okay.
So, okay, cool. Any other last thoughts or questions on this? There is a nice, so look at figure, just to kind of bring it back to the local area, figure 10, which is this multi-figure. And part D
Good cause.
is Southeast Alaska. And just to kind of, I think it's a good thing in this class in particular and overall just to kind of be familiar with what's happening there in terms of blocks and because you will if you go to presentations here by some of our structural geologists or this or that, there's a lot of people that will end up referring to this Yakutat block and the mountains there, the St. Elias Mountains, which are really high. So you will probably see a lot of this.
Yeah, honestly, I didn't know that it was like a transform and subduction down that area. I had no idea until
Yeah.
this class, honestly.
It's a cool little, so you've got the Aleutian Trench, which can generate some pretty big earthquakes. The Yakutat block is this funky little thing that's kind of stuck in there and rotating around. And then what I like about this simple diagram is that you can see the relationship between the Aleutian Trench and the Denali Fault, which is the other place we get big earthquakes. There's of course, as with all of this stuff, there's some debate over like how old the Denali Fault is and all sorts of various things and what the kind of longer term relationship is and how the Yakutat block fits in that. There's a lot of neat stories in there though in terms of just mountains that we see all the time when we think about like how Denali itself fits into this picture is not quite as clear as you would think. So there are some multiple net stories that are just about this landscape that we're in right now. Any other?
I
Yeah.
have kind of a off-topic question, but the continuum models, are those usually applied using finite element analysis?
Yeah, you can do it. So we will eventually get into more of this, but you can do it using a finite difference type technique if you make assumptions. Like I think he mentioned briefly the idea of a thin viscous sheet
Mhm.
model,
Mhm.
and what that's saying is that basically there's uniform properties with depth, and that this thickness h, or height, we use h a lot for that, is really small compared to the distances that you're interested in. So if you're interested in hundreds to thousands of kilometers, and you're going to assume this as, 30 kilometers, however thick you want to assume it is, it's really skinny compared to the extent that you're looking at. You pretty much, it's the difference in properties in this direction are going to be much less important than the difference, like the viscosity here versus the viscosity over here that you assume is going to be way more important than your viscosity up here versus down here. And so what you can often do is, even if you know there's a bit of a viscosity difference, you would come up with what you might think of as the best bulk property for the whole thickness. And then that might vary spatially this way, but as long as this is thin compared to the whole extent that you're interested in, then it can simplify the math down a lot such that you can do it in more like a finite difference kind of a model if you need to. So you can do models that aren't that complicated in terms of the computing. But then at some point, most of the time, if you know how to put together a finite element model, that ends up being the most effective. So yeah. But again, this comes back to what is your question, and the more complicated your question is, and the more data you're trying to integrate, the more likely you might have to go to a finite element type situation. And you might even use a finite element model with this type of a thin viscous sheet. But you'll see that we will do some very simple, just analytical solutions that are getting at some of these things. And so it is a continuum model, even if we're solving it analytically, because the assumptions we're making are analytical. The assumptions we're making are that it is behaving as a continuum. So you can do a continuum model with the analytical solution is actually more the true continuum model, but then a lot of times we discretize it in order to put it into a computer. And then you do have to come down to questions. If you are putting it into a model, you have to be very careful about how you break it up into the elements for your finite element or your finite difference model. Because if you make these too big, depending on the time scale that you're trying to solve, it won't be a good model. And so once you get into the computing side of it, you actually really are taking a block model down to tiny blocks, because that's really what a finite difference model or finite element model is it's saying there's these little blocks, and we can figure out how they interact with each other on this tiny scale. So we will mostly be doing analytical, relatively simple versions of the models in this class, but they can always be scaled up, and you can bring in a computer to help solve it. And we will at one point, I think the third, unit 3, we'll do a finite difference model for looking at temperature distribution with depth. And that'll kind of introduce you to how a finite difference model works. So we don't quite get into finite elements in this class because they're just too complicated mathematically. If you need them, you'll be able to, you'll take the time to figure them out. Okay. Any other last questions or ideas? No? Okay. Then we have half an hour left to dive into, as we just concluded here, the material properties are actually quite important. And there are ways to simplify, at least conceptually simplify, and mathematically associate with these. Let's see. How many of these do I have? Gotta love Slinkies. So each, actually I do have more of this. You can do this in pairs, or if you want to, I have more of those Snickers bars. Those are great for the ductile versus the brittle crust in the ductile deep down. So you need at least one Slinky, yeah, 2 pencils, 1 Slinky, and this, if anybody else wants to do one more. So and this will just, like, some people really, it's really helpful for them to get their hands on and like move things around. Other people are fine just staring at equations. So feel free to use those as you can. A few things that we talked about already, right? We talked about taking lengthening of a beam of something. So we apply a force. Remember, this is how we got to the force, the stress, because we looked at the force over the area. That was our stress. And if we lengthened it, we got to our strain, which was the change in length over that original length. And so we got this far last week, but it's this relationship between the stress and strain that depends on that material property. And so you will see this, a lot, this concept of relating the stress to our strain, and our strain or the strain rates are ways of describing the deformation. So what's the simplest material property that you guys can think of? How would you describe the spring there?
The elastic coefficient.
Yeah, it's just an elastic material. So in that case, you apply a stress, there's a constant of proportionality, and you get a certain amount of stretching from it. So it's totally linear. This is a classic, it's often called a Hookean solid, or just a basic elastic material. And this is Hooke's law, and the constant proportionality is is called the elastic modulus, or it's also called Young's modulus sometimes.
It's also linear in certain boundaries, not forever.
Well, yeah, so this way that we describe it does make it look like it's linear forever and under certain boundaries. And something else, like, if you apply that stress, does it, in real world, do you get exactly an instantaneous response? If we're talking about actual real materials, so the elastic process, what is happening at the crystal scale on that? Like, what's happening to, if you imagine that each one of those rings is an atom in a crystalline structure, what's happening?
I imagine they're
spreading
getting
out.
they're getting pulled further apart. And
Yeah.
their bonds. I
So
think
you're
their-
stretching the
their bonds
bonds.
just wanna go back together.
But I don't know if the
That's like
elasticity
a
of the
spring
spring is from
bonds.
its structure, not from the crystals, right? This is a specific shape. If I took the same metal and put it in a pipe, I wouldn't get this
You would
elasticity.
get a different elasticity. You're right.
So it is
yes.
structure, not the crystal size.
Well, for this, the spring is kind of the classic. The spring is a classic structural version of elasticity, but that metal will also have an elasticity by itself.
Somewhat, but this is not representative of the metal crystal.
Not the metal. No, it's not. So the spring is a model that we use to think about
Sure.
elasticity.
Yeah.
It's not. So the spring, if these are our molecules, the spring is just kind of representing those bonds between the molecules, and you're stretching those bonds, but are we breaking them?
No.
No. So as long as we don't do it too far, if we don't stretch it too far, then we're not breaking those bonds. They stretch and then they go back. And that's what elasticity is that we're stretching those bonds, but we're not breaking them.
Is it still elastic if they don't go back?
It's non-recoverable,
Okay.
and so it's often not considered purely elastic. in that case.
I'm sorry. I'm not totally convinced we're actually extending metallic bonds and when we're doing these things. I mean,
It has
Um,
nothing to do with the material.
but we were saying now we're changing bonds.
We're
It's
stretching the bonds within the material.
Yeah, I think you are pulling the bond distance apart, and the bonds, like the lattice structure, I think wants to go back to
The
where it's
lattice
at.
structure tries to go back to where it wants to be.
But you're
What are you?
It seems to me that would require a lot of energy to. So first of all, when you expand something like the putty, I think it. So it thins out in the center. Why is that happening?
Is it so when you expand that putty? Is that purely elastic?
I don't think so.
Right, it's not. So with the silly putty, it's not just. It does have some elasticity. You can ball up your silly putty and you can bounce it, and it'll respond. It'll spring back, and it won't change its shape dramatically during that time. That would be the elastic
Sure.
behavior of the silly putty. And that is, in the silly putty's case, it's a polymer, and so
Right.
it's a bunch of twisted strings
Molecules.
of molecules. And in that case, you're sort of stretching them, but you're
But it's distance between molecules versus this is a continuous lattice, which to me is like, I don't know, I'm having a hard time thinking of a solid lattice being stretched just by somebody like, I mean,
ice, rock.
but ice is in a specific, I mean, ice that happens only in close to the melting temperature.
No, you can send a seismic wave through ice at any temperature. You can send a seismic wave through rock at any temperature. And what's a seismic wave?
Compression and extension.
Pressure wave.
Yeah. So a seismic wave is actually, we're stressing those bonds, we're stretching them, and then they relax and they stretch.
Okay,
and
Are you
well,
saying
yeah.
it's
So,
too
like,
much energy for
when-
just our hands to do?
Yeah, okay.
Well, so like when you stretch out a spring, it actually the metal stretches out and it actually gets colder.
I think it gets warmer, no?
No, when you stretch it out, it gets colder. It seems to be a
There's, I mean, so you can have, in a purely elastic material, it will recover its shape exactly, and you will recover the energy that you put into it. So it takes energy to stretch a spring, but then you get that energy back when it tightens itself back
Rubber
up.
bands, good example.
A rubber band is the same way. But when we get into the real world, very few things, maybe nothing, is really purely elastic. And it is true, and there's subtle differences in how that elastic behavior is expressed. So in air, you can also send an acoustic
Sure.
wave through air.
Sure.
And that's not necessarily about the bonds between the molecules stretching, but it's the changing
Collision.
pressure, that's the amount of collisions happening
Sure.
between. So it's a slightly different molecular scale process going on, and so this bond stretching is what happens for a crystalline solid. So that happens for rock, it happens for ice, it happens for metals. Polymers, again, it's these like twisted strings of molecules, and there might be some stretching of bonds, but it's also about tightening those bonds and twisting them against each other. But like you can see with the silly putty, polymers like that are not often purely elastic. They're rarely express that pure elastic, because they don't have that kind of structure. And then a gas has this, the temperature of the gas and the vibration, the excitement of the molecules is what helps control this elastic constant and how much it's going to respond back and forth. And we will, when we get into the unit 3, we will come back to the purely what's happening much more on the molecular scale for rocks, and which is the most common material that we think about in this class anyway. Rocks and ice, which is a rock. So this is the pure elastic process. The pure viscous, what is the relationship? What happens when you stress a purely viscous material? Like water, which we say has a constant viscosity.
It deforms at a constant rate.
It deforms at a constant rate. So instead of it being that the strain, which is our net end result of the stretching, is related to the stress. In this case, I did that backwards. The strain rate, actually I think I did have it right. I always do this. I do write it the other way. The stress is related to the rate of strain. So d epsilon dt, it's the rate of strain.
What is that symbol beside strain?
Viscosity.
Oh,
This is,
Ah,
so in this class, and I do want to
Viscosity,
say this because you will
gotcha.
see this done differently. I try to be very consistent in using mu for elasticity and eta for viscosity.
okay.
Sometimes those are used differently. So you might see mu used for viscosity in other people's papers. They can be used differently. So you should be able to look at the between the context that it's used in, know whether or not it's being used as a viscosity or an elasticity. But in this class, I try to keep it, I try to be very consistent in this. But you should just know for yourselves that it can be different. So in this case, for a constant viscosity material like water, we apply a stress, which might be like letting it run down, allowing gravity to pull it down slope. Then it will have a constant rate of strain. That means that you don't get back. If you pour water down a slope, and then you stop applying that gravity to it, you don't get back the deformation that you caused. So this is non-recoverable deformation.
What is viscosity units?
They're in Pascal seconds, which you can actually see here because this is in
Where are you pointing? Oh.
Pascals is a stress,
Mm-hmm.
and strain rate is 1/seconds.
Okay.
So the units, there isn't, this is kind of the standard Pascal seconds for a uniform viscosity like this. But like with the silly putty, it's got both elastic and viscous stuff going on. So this is where we need to get a little more creative mathematically, because we cannot represent most materials as purely elastic or purely viscous. It won't get us what we want in terms of the material. And also, you can run into a lot of different variations on viscosity where it's not constant. It depends on temperature. It can depend on the composition, and this is true actually of the elasticity. So mu and eta can depend on temperature. They can depend on composition. They can depend on pressure. If it's under pressure versus not under pressure, that'll change. For example, seismic waves travel differently in rock, same temperature, but if it's under pressure. Eta can also be dependent on the stress level, which just complicates this whole equation up there, doesn't it? If eta is then stress dependent. Or it could be strain rate dependent or strain dependent. So you can actually have a lot of complications in here, but we try to keep it relatively as simple as you can, as necessary. So sometimes if eta is stress dependent, we might write it the other way around, where epsilon dot is equal to 1/, let's just call it some A times, say, sigma cubed. In this case, eta is actually equal to A over sigma squared. I think I did that right. So if you stuck A over sigma squared into this equation, rearranged everything. If you took this, stuck it into this equation, and rearranged it, the sigma squared would come onto that side, and you get the 1/A. So you will sometimes see it written that way. They may or may not make this explicit relationship here when they write it this way. They might just write it this way, and you'll be like, wait, what happened to the viscosity? There's no eta in this equation. The reason that they don't do this is that when we use eta, we often are assuming that it's constant in that situation. And so if it's not going to be constant because it's dependent on stress, sometimes we just leave eta out of the whole discussion and just write it in terms of that A factor.
What is A in that?
It can be called a bunch of different things.
But it's just like a constant.
Softness parameter.
Oh, like just a regular or a
It's some kind
coefficient
of
of
a
some sort.
coefficient that's helping describe the viscosity. Sometimes, you could use B, you could use whatever. Mm-hmm.
Is there any other examples for non-recoverable object for this case besides water?
Well, the silly putty. And if you get on different time scales, so you can imagine that, so why, this has been in my office for the last year. What happened to the rubber bands?
They lost their elastic property.
They lost their elastic properties. So through time, you can have a change like that. So we think of this as being elastic on a short time scale, but when the material gets old, it's going to change, and it might then, and if you leave it held out, stretched for a long time, then even though we don't think of it as being viscous, it's got just enough viscous in there that it doesn't spring back eventually. But it's such a subtle viscous thing that you don't notice it for a year or more. Same thing happens with paper clips. A brand new paper clip, you stick it over your bunch of papers, and then you pull it off, and it's going to spring back and do all nicely. But if you stick it onto a pack of papers and it sits there just slightly open for a long time, then the next time you pull it off, it might not close all the way. So there's just enough of a viscous effect going on there that you have some non-recoverable deformation happening. Which is why what we do in order to try to combine these behaviors is that we model them as being a combined behavior. So this is what you can do with the pencil. So if you take you can you should do one or both of these. So take the two pencil. This is your slinky. And in this case, we're moving these slowly enough that your silly putty is mostly going to be viscously deforming. So silly putty is one of these things that if you turn the ball and bounce it, it's elastic on a short time scale. But if you just start pulling on it, it behaves more. It behaves more viscously. So if you take for the more linear one, you don't having the pencils isn't quite as critical as for the other one. But if you take this setup and you instantaneously apply a force to it, what happens?
The slinky moved?
The slinky moved first, but what's happening now?
Oh, it's pulling slower. This rate is slower on the silly putty.
Yeah, so the slinky is transferring its stress onto the silly putty. And if we wait long enough, what do you think will happen?
It'll either stretch out or break.
Yeah, in this case it looks like it's breaking because it's not stretching very uniformly. But eventually, if we wait long enough, the slinky is going to totally be back where it started from, and all of the deformation all of that stress will have been transferred to the silly putty and deform the silly putty according to the stress that we applied.
So why was that difference? I'm missing. Why is one behaving badly? So why was the energy transferred to the spring first and not the silly putty?
Because
It might just
because the slinky, because it's elastic, it can act instantaneously to a given stress. So remember
Did you say
that.
both are elastic? Oh, I see.
No. The silly putty is not behaving very elastically.
Okay.
So the slinky, here we get an instantaneous amount of strain. So if we apply a stress,
force.
we get an instantaneous amount of strain out of that. And this initially has, so let's do this. So we have a strain, and we have, sorry, I'm gonna do this, time. So we apply stress at time 0.
There
We
go.
immediately get a certain amount of strain from the slinky. But then slowly, that strain gets transferred onto, and this is actually a slightly, this actually would apply if I were this is actually a slightly different version than what I just did with my hand. Because what I just did with my hand is actually I applied a certain amount of strain. I did a fixed change in length. And then allowed the system to adjust to that. Do you guys see the difference in what I'm saying?
But you said the strain was instantaneous. I'm not sure.
The strain is.
Are you saying that the strain is not described in the plot? That's what you're saying? Or? I'm not sure.
Yeah, I'm gonna get rid of this for a second. I'm gonna erase that for a minute. Because there's 2 things that I can do with this setup. Actually, for the moment, I'm gonna get rid of this guy. So if we apply a constant stress, then the spring is going to give us its immediate strain. The viscous silly putty is slowly going to give us additional strain. So this is the version where we start applying the stress, and it's actually a little bit harder to create this. Because in order to keep this spring at the same amount of stretch, it's trying to relax, but what I want to do is slowly just try my hardest to keep the spring at the exact same stretched amount. But to do that, I have to constantly change the stress. I have to keep the force here going so that I'm moving my pencil out because this is responding. So the stress across that system stays the same, but the strains add through time. So this is our strain that is adding through time. So this is our elastic spring, and then this is our silly putty. The other one that I did first, I actually gave it a set amount of strain, so I lengthened it by a set amount, and I kept that constant. And what happened then, in that case, we want to think about, well, what was, and this is where, if you do it yourself, you can get a better sense of it, how the stress changed through time. So initially, I had to give it a certain amount of stress to get the slinky to expand. But then as that stress caused slow deformation of the silly putty, it relaxed the slinky. Eventually, the entire system came back to 0 stress. So if I sat there long enough, then my hand, I wouldn't have needed to put any force on the system to keep it at the final total length. And that's because the viscous behavior is permanent. So as long as, like, it gets there, but once it gets there, you don't need to add more stress to maintain that. So at the end here, we're maintaining all of our strain because of without any stress, because it's the viscous deformation that got us there. And this is a slowly, gradually changing system like that. So mathematically, we can look at this as we have here mu, the stress equals mu times epsilon, and here the stress is I keep doing this. The stress is eta times the strain rate. And the stress among the two objects adds together, plus eta times epsilon dot. So the total stress I apply causes this plus this. So initially, all of my stress is going into this to make that initial stretch of the slinky. But through time, this starts deforming, so this stress decreases, and this stress decreases and transfers over and deforms this. It deforms the viscous fluid. Does that kind of make sense?
Yeah.
This is
And to keep that equation, that's why you had to hold it to expand, because you wanted that to
yeah,
stay.
this is if we keep a constant stress. So we're adding together the strain. Right. I'm just gonna, yeah. So the trick here, if we apply a stress to the system, then we call this a creep experiment, and we are applying a set change in stress, and we see how the system responds to that.
Is that applying a stress?
Yeah,
or
because I just didn't write that word. Applying stress. But then if we apply a strain, a step change in strain, it's called a relaxation experiment. In this case, it's the two stresses that get added together, so when you solve these equations, applying because this now is a differential equation because we have, it's a little more complicated to solve because we have the differential of the strain and the strain in the same equation. So this is why they're not all analytically solvable once we get things to be more, this one is, but not all of them are. What we end up with, if we apply, let's make sure I write this down right, this part is in your notes. Oh, dude, and I'm not, I had too much coffee this morning. Because this, I actually did this part wrong, so this is this one, the strains add. So the lengthening is the total length of adding both of them together. So we have to say the strain rate is equal to
So that other formula you put up there is not right.
It's for the other version that we're going to do next, and I just got a little
Okay.
So if we put them side by side, I'm sorry, and this is where you do need two pencils. If we can get this on better, I would recommend opening yours up and doing this, because that'll, so if you do them side by side like this, I can get that to hold on. My hands are applying the same amount of stress on both in order to keep the pencils parallel. I'm applying the same amount of stress on both. Whereas in this case, what I said was right, that the stress starts out being all on this guy, but gets transferred over to this guy. It's the net length that you add together mathematically in this version. Because we're adding the length of this to the length of this in every situation. So, anybody ever taken an electrical engineering type class and know what series versus parallel is? This is series versus parallel, the same concept. So the other one, we draw just like this. So this is the series one where we add the strains.
I was wondering what the circuit diagrams and the notes were all about.
Yeah. And you can, there's a lot of parallels actually to the way circuit diagrams work. So in this case, the strains add, but in this case, in the parallel case, the stresses add and the strains are going to be a little bit different. In the electrical world, the stress is like the voltage, and the strain
stress would be the voltage.
Stress would be the voltage, right?
But I'm not.
The current doesn't.
Yeah, I think there's some.
The current doesn't make sense in that sense.
I guess if you had two different resistors and current would go to the lower resistance
I
and
think
the other,
voltage is
then
the
you can.
strain,
Yeah.
and
I
current is
yeah,
the
'cause
stress in this case. It's a little, but in our case,
stress is constant and it's not yet.
so here the strains combine, and here the stresses the total stress that you have to add I guess in multiple places or too many places.
In series, wouldn't it be that so the strains are added together and the stresses are equal on both of them, whereas in parallel the stresses add together and the
Right,
strain
and
is
the
equal
strains
across
are
both.
equal across both of them. Exactly. So here we can add our strains. Oh dude, we're past time, sorry about that. So we can take, the end point of this is we can take each of these components, and if we make sure to add them in the right way, we're adding strains here, we're adding the total length is the sum here, with the stresses distributed equally across them. And in this case, the stresses add. We can start to build up behaviors that can mimic both elastic and viscous at the same time. So we will use that. That's how you mathematically start to combine and create a material that has both effects going on. So we should end there, and sorry for not keeping track of the time. I got distracted by the
High five when you're having so much fun in geophysics, right?